Hi, I am Revati. I am pursuing my Master's in Construction Engineering and Management at CEPT University. This semester, for our studio Construction Project Execution, Monitoring and Control, our project is a high-rise commercial tower. The project is located in the Gift City SEZ zone, which is one of the most rapidly developing business hubs in India. The structure consists of 3 basement, ground floor and 24 upper floors. The total site area is around 7,000 square meters with a typical floor plate area of 3,123 square meters. The total estimated project cost is approximately 143.27 crores. The RCC works are executed through square foot based contract, while finishing works are executed through item rate contract. The project commenced on May 10, 2024 with an overall timeline of 24 months. This presentation covers important aspects such as site layout planning, port planning, reinforcement planning, material management, job hazard analysis, and contract administration. The layout planned to ensure sufficient movement of material, workers, and machinery while maintaining safety and productivity on site. The separate areas were allocated for steel yard, bar cutting and bending machines, QA/QC laboratory, machinery parking, material and passenger hoist, labor entry, and climbing tower crane operations. The project uses 2 water sources. First is the municipal supply from Gift City for construction activities, and second is an independent borewell for labor colony and sanitation purposes. For water storage, underground sump with a capacity of 50,000 liters are provided for curing and site activities. Separate drinking water tanks with a total capacity of 6,000 liters are also maintained. The daily site water consumption is approximately 30 kiloliters, while the labor colony demand is around 26 kiloliters. For electricity planning, the total power demand from equipment, offices, labor colony and steel yard is around 172.5 kilowatts. Based on 10 working hours per day and 26 working days per month, the estimated monthly energy consumption is around 44,850 units, resulting in a monthly electricity bill costing of approximately 6.27 lakhs. Proper site planning helps in improving the workflow efficiency, safety, and overall coordination on the site. This slide explains the pore planning and reinforcement processing productivity. The slab area was divided into 2 equal pores, each covering approximately 1,561.66 square meters. This division helps in maintaining better quality control and smooth execution during concreting. The slab cycle duration for each floor is maintained at 15 days to ensure continuous construction progress. For reinforcement processing, the project uses 2 bar cutting machines, 3 bar bending machines, 1 bar threading machine, and 3 fabrication teams. The daily and monthly capacities of these machines were calculated to ensure uninterrupted reinforcement supply. The bar cutting machines provided a monthly capacity of 156 metric tons, while the bending machines provide around 195 metric tons per month. Based on productivity calculation, reinforcement activities require approximately 66 workers. The project uses Spartan SB55 bending machines and Spartan SCM 42 cutting machines and Spartan HGS40 threading machine. Effective pore planning helps improve labor productivity, maintain slab cycle timelines, and ensure timely project execution. This slide presents the reinforcement planning and steel yard management. Major reinforcement components considered in the project include beam reinforcement, column reinforcement, shear wall reinforcement, and slab reinforcement. The quantities for each reinforcement components were calculated based on structural requirements. For example, shear wall vertical bars weigh approximately 312.84 kilograms. Slab main bars weigh around 148.08 kilograms and column vertical bars weigh around 97.81 kilograms. The steel yard was planned using the thumb rule that 1 metric ton of steel requires approximately 1.5 square meters of storage. Considering the peak steel requirement of 315.5 metric tons, the required steel yard area was estimated at around 473 square meters, and a total area of 500 square meters was adopted. The steel yard includes dedicated zones for raw steel stacking, cutting, bending, threading, and welding, and finished steel stacking. A detailed bar bending schedule was also prepared to specify bar marks, diameters, spacing, lengths, and total weights of different structural members. Proper reinforcement planning minimizes the material wastage, improves workflow continuity, and ensures smooth execution of RCC work. This slide explains the material management approach using the EOQ model for reinforcing steel. The annual steel demand for the project was calculated as 3,786 metric tons. The purchase price of steel was considered 50,000 rupees per ton, while both ordering and carrying costs were taken as 5,000 rupees. Using the economic order quantity formula, the optimum order quantity was calculated as approximately 87 metric tons. At this EOQ value, ordering cost and carrying cost became equal and the total inventory cost became minimal. The analysis showed that approximately 44 orders are required per year, with an average gap of around 8 days between each order. The total inventory at EOQ was estimated at approximately 18.97 crores. The study also showed that lower order quantities increased procurement frequency and ordering expenses, whereas higher quantities increased storage and carrying cost. Therefore, EOQ analysis helps achieve economical inventory management and improves overall project efficiency. This slide explains the HERA register prepared for the project. Different construction activities such as welding, electrical work, diesel handling, concreting, scaffolding, and work at height were analyzed to identify potential hazards and risks. Some major hazards identified include fire hazard, electric shocks, fall from height, machinery accidents, and health hazards due to chemical exposure. For each hazard, suitable control measures were proposed such as PPE usage, fire extinguishers, RCCB protection, insulated cables, quadrails, safety nets, and proper inspection. An EHS organization structure was also established for effective safety monitoring that includes the AGM EHS, and a site lead EHS, and a senior EHS engineer and assistant EHS engineer. The HERA study helps reduce accidents, improve work safety, and ensure safer environment and construction practices on site. This slide presents the prevention cost analysis for site safety measures. Prevention costs include expenses incurred to reduce accidents and improve overall site safety. The major safety items considered include helmets, safety vests, safety boots, gloves, safety belts, welding shields, safety nets, and safety screens. Among these, safety screens contribute the highest share of preventive cost. The total prevention cost of the project was estimated approximately 2.1 crores. In addition to equipment costs, labor safety training and EHS monitoring costs were also considered. Regular safety supervision and implementation of preventive measures help reduce accident-related losses, improve worker awareness, and maintain better productivity on site. This slide explains the contract administration procedures followed for the project. The project includes various contractual provisions related to payment terms, retention money, mobilization advance, liquidated damages, price escalation, and variation management. Monthly RA bills are submitted by the contractor and verified through multiple stages before the payment releases. The RA billing process includes preparation of bill submission to the client, site verification, head office verification, account processing, and final release of payment. The retention money and mobilization advance deductions are also made during the billing process. Proper contract administration ensures better financial management, documentation control, stakeholder coordination, and smooth project execution. This slide explains the extra items identified in the project, which is waterproofing work. The waterproofing scope includes foundations, basement, ground floor, and other water-prone areas. This item was not included in the original BOQ and was therefore treated as an extra item. The requirement arose to protect the structure against seepage, leakage, and long-term durability issues. The extra work was considered technically necessary and fully admissible under variation management procedures. The cost implication depends on the waterproofing area and applicable materials and labor rates. Proper variation management helps in handling additional works effectively while maintaining contractual transparency and project quality. To conclude, this project demonstrates the importance of integrated planning and management in high-rise construction projects. Through proper site layout planning, reinforcement coordination, material management, safety planning, and contract administration, the project achieves improved productivity, efficient resource utilization, and enhanced safety performance. The study also highlights how systematic execution and monitoring practices contribute to smoother project delivery and better construction management. Overall, these planning and management techniques form an effective framework for successful execution of large-scale commercial construction projects. Thank you.